Welcome back. My name is Matthew, and in this video we're going to talk about sum and difference formulas. And these are, in the truest sense of the word, formulas, and we're going to see some different ways that we can use them, and we might even prove an identity or two like we did in the previous video. Let's have a look. At the top of this screen is a set of formulas. And this is sort of a formula-heavy chapter that we're moving into. So we need to be mindful of that and be sort of using all of these or many of these formulas as we're going through this body of material in what this author, who I sort of borrowed these notes from, Stewart, calls Chapter 5. And my students are going to get a formula sheet that they get to work with that will have, I think, all of the formulas that you see printed on these printable notes. And those formulas are available to them. Where are those? I think they're in the reviews section where you're doing your homework. In that left-hand navigation column, click into reviews and see if associated or right nearby the reviews, if there's a link to a PDF of the formula sheet. And then I want my students using that formula sheet while they're completing their homework assignments as practice for using that formula sheet in order to complete quizzes and exams, because they will get to use a clean version of that formula sheet on the quizzes and exams. For those of you who are not my students, a quick screenshot of this and you could sort of build your own formula sheet. But what I'd like to do is use a sum or difference formula in order to find the exact value of this expression that we're seeing in example 1. And you'll notice that this says cosine, cosine plus sine, sine. So what I'm doing is looking up here into, into this blue box, and I'm looking for a right-hand side, in this case, of an equation that says cosine, cosine plus sine, sine. And I've spotted it. It's the second one here, cosine, cosine plus sine, sine. Yep. So the alpha value is the 5/18 pi, and the beta value is pi over 9. And the left-hand side of our equation tells us what we're going to need to do is alpha minus beta. So let's do that. This is equal to, and if you want, you could label these as alpha and beta, and alpha and beta, and this is going to equal the cosine of alpha minus beta, which is equal to the cosine of 5 pi over 18 minus pi over 9. I will do a quick common denominator for us. This is the cosine of 5 pi over 18 minus 2 pi over 18, resulting in an almost final answer of the cosine of 3 pi over 18. I say almost final answer because we're going to be able to reduce or simplify the 3 pi over 18 and write this as the cosine of pi over 6. Now we could stop there, except that this problem has instructions that say find an exact value, and I'm capable of evaluating the cosine of pi over 6, and you should be too. This is adjacent over hypotenuse, low in the first quadrant. A final answer of root 3 over 2 would be ideal. In the next problem, we are working starting with the other side of the equation. Here we have the sine of alpha minus beta. So we need to go up to our formulas again and see on the left-hand side, can you find the sine of alpha minus beta? I think it's number 4. So we have to take those alpha and beta values and drop them into the right-hand side of that equation. This time it's sine cosine minus cosine sine. Sine cosine minus cosine, that's an alpha, sine, and that's a beta. Now let's drop in these values. We've got the sine of 60 degrees times the cosine of 45 degrees minus, I just talk my way through it because otherwise it's too quiet. It makes me uncomfortable. I was thinking and writing and talking at the same time. Can I write the number 45? Yes, thank you. Little degree symbols on there if you want, whatever. And then I'd like to evaluate all of these functions. So the sine of 60 degrees is high in the first quadrant. Sine is opposite over hypotenuse. That's a root 3 over 2. And the cosine of 45 is in the middle of the first quadrant. We've got adjacent over hypotenuse. That's a root 2 over 2. Minus cosine of 60, that's a 1/2. Sine of 45 is another root 2 over 2. And this simplifies to this is so weird. Look, one way that we can put these things together is the square root of 3 times the square root of 2 makes the square root of 6. And over here, the 1 times root 2 makes the square root of 2, so minus the square root of 2, all divided by our common denominator of 4. This is one way that you could write the final answer. I have seen it presented. I've seen the final answer presented like this. This square root of 2 gets factored out of the numerators so that the final answer is written, I think it's written as the square root of 2 times the square root of 3 minus 1 all over 4. And for some reason, that's the most simplified version of the answer. I don't know. You have to know your audience. In this case, my students have an audience that's a computer because that's where they type in their homework assignments, as most of you do. So be sensitive to the fact that the software you're using was programmed by a human who was just following orders and programmed it the way they were told. And if they were told you're supposed to factor out the numerator as far as possible, then, well, then this is the correct answer because we factored out the root 2. I think it's silly. Well, this is different, finding the sine of 75. I don't know how to find the sine of 75 degrees. Maybe we could use a sum or difference formula. Can we write the angle measure 75 degrees as the sum or difference of two angle measures that we're more familiar with? 75, that's 30 plus 45. That works. And I forget if it was the sine or cosine function, but so we're going to be using either 1 or 4. Let's just pop down and see what that was. Sorry about that. It was the sine function. So we're going to use the sine of alpha plus beta. That's equation number 3. And it's sine cosine plus cosine sine. All right. Let's set it up. This is, how should we write this? Maybe we'll write it like this. It's equal to the sine of 35 degrees plus 45 degrees, which is equal to the sine of 35 times the cosine of 45 plus the cosine of, the 35 is supposed to be a 30, of course. Cosine of 30 times the sine of 45. Let's make that little correction in there. That's supposed to say 30. Yep, that looks good. Okay, and then we have to march through and evaluate these functions. So identifying the correct identity to use, sum or difference formula, is part of the process. And then evaluating all of these things is a distinct part of the process. And if you're not really good with the unit circle, or as my students had to take speed quiz and be able to evaluate these trig functions pretty quickly, this is going to be labor intensive. You don't want to be punching these into a calculator either, really, because, I don't know, like the cosine of 45 is root 2 over 2. It's going to come out as an ugly decimal. Once you learn what the decimal is that corresponds to the exact solution, This is going to be kind of irritating and time consuming. So let's knock these out. Sine of 30 is 1/2. Cosine of 45 is, we just said, root 2 over 2. Cosine of 30 is root 3 over 2. Sine of 45 is root 2 over 2. And we've got this weird situation again where maybe we're supposed to factor out the root 2. Let's do that first this time. It's the square root of 2 times 1 plus the square root of 3, all divided by 4. Or we could multiply that in and get the square root of 2 plus the square root of 6, all divided by 4. So either one of these is a viable final answer. A little bit of creativity deciding to write the 75 as a 35. 35 plus 45. You could have said something when I wrote that. Y'all got to look out for me. 30 plus 45. Now I'm paranoid. I'm double checking the rest of my work. Yep, the rest of that looks good. Okay. Moving on. Cosine of 105. This is not an angle measure that we're familiar with, so we need to figure out a different way to write the 105. Could we write it as the sum of two angles? Absolutely. 60 plus 45, that works. Could we write it as the difference of two angles? What's 3 pi over 4 in degrees? What puts us in the middle of the second quadrant? That's 90 plus 40, that's 135 degrees. Oh, 135 minus 30. That would do it. And that might be a nice exercise for you to evaluate a couple of trig functions in the second quadrant instead of just doing everything in the first quadrant, because we need to keep up on that skill. So see what you can do about solving this one. Maybe do both of them. Do it as where you change the angle measure to 30 plus 45, and then redo the problem where you change it to 135 degrees minus 30 degrees inside of the cosine function. Use the appropriate sum or difference formula and grab your alpha and beta values and go through and come up with a solution. And your solution, my guess, is going to look, something like one of these previous solutions that we've gotten. Excuse me. And then how are you supposed to check your answer? He's just leaving us here with this empty piece of paper. How are we supposed to get an answer or check our answer? If you get an answer that looks something like this, punch it into a calculator. I have a calculator. Now I'm interested. Now I want to check my own work. See what you've done? I'm using my TI-84 Plus graphing calculator. The first thing I'm doing is hitting the mode button near the top left, and I'm dropping down 2 clicks and 1 to the right in order to highlight degree, and I'm hitting enter to put me in degree mode. And then I'm doing second quit near the top left in order to get back to the home screen. And then I'm typing the square root of 2, and then I'm coming out from underneath the square root symbol using my arrow key. Then we have plus, second, square root. The square root button's in the left-hand column, by the way, about halfway up. Square root of 6, right arrow to get out from underneath there. And then I'm going to hit enter. And I've got 3.8637. And then I'm going to hit divided by 4 equals, and I've got 0.9659. How does that help me determine whether or not this is the right answer? Because the next thing that I'm going to do is still in degree mode. I'm going to come up here and I'm going to type the sine of 75. Enter. You will not be surprised to find out you can't read this because it's not in focus. Can we get it there? Nope, that's the wrong direction. Scoot it over. Get it together. Oh yeah, right about there. Obviously, I don't have autofocus on the camera that I'm using. Those are definitely the same numbers. Wouldn't it be nice if I had the ability to make that window larger? Bam! Now even I can tell that they're in focus. And you can see what I did. And I figured out that if I lower the brightness on my calculator screen, you can actually see it and it's not all blown out. Cool. So that's the kind of thing that you can do also in order to confirm whether or not you're getting right answers after using the sum and difference formulas. I'm just blurry and packing up my calculator here. Let's turn that off. Let's make me small. And then let's get our focus back. So you can really practice any of these problems on your own by using a calculator to get the decimal solution to this, and then do a little arithmetic to get the decimal equivalent of whatever solution you get, and then compare the two. So we looked at sum and difference formulas for sine and cosine. Now we're going to look at them for tangent. And these are a little bit more complicated looking because the right-hand side, instead of it being sine, sine minus cosine, cosine, or something like that, instead of a product, here it's a fraction. Not so bad, and again, my students don't have to memorize these, so that's nice, but you know, if it's plus here, and it's minus here. And if it's minus here, then it's minus here, and it's plus here. Good news is also on the right-hand side of this equation, it's tan alpha and tan beta, and tan alpha and tan beta. That's only two evaluations of functions that you have to do. In those previous sum or difference formulas with sine and cosine, you had to evaluate 4 different functions on the right-hand side every time. So this is a little bit less work, which is great. Now look at example 2. It's the tangent of, clearly it's alpha minus beta. And what am I going to do with this alpha value and this beta value? I'm going to plug them in up here into that entire fraction. The left-hand side of the equation equals the right-hand side of the equation. The tangent of a difference is equal to whatever that fraction turns out to be. We can leave the alpha and beta there. Okay, so this is equal to, it's the tangent of our alpha value, which is 5 pi over 3, minus, I don't like the way I wrote that. It was too high. 5 pi over 3 minus the tangent of our beta value, which is pi over 4, all divided by 1 plus, and again, the tangent of 5 pi over 3, this time times the tangent of pi over 4. Match up these components, right? Alpha, 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 there they are. There's a beta, here's a beta, there's a beta, there's a beta, there's a beta, there's a beta. Right, they're all accounted for except I skipped an alpha, so now I've got to go back. There's the other alpha. That wasn't the right color pink. Alright, so everything is matching up and accounted for. Great. Now we have to start evaluating trig functions, these tangent functions. What is the tangent of 5 pi over 3? 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3 is low in the 4th quadrant. Tangent is opposite over adjacent. That's negative root 3 over positive 1. Minus the tangent of pi over 4. Pi over 4 is in the 1st quadrant. That's root 2 over root 2, or however you do it. Some of you watching this video might be actually using the unit circle with a radius of 1. In my class, we don't do that. We use a 2-unit circle with a radius or a hypotenuse of 2 so that we don't have all the fractions that you guys have to deal with. Not to say we're better than you, we just exercised a little forethought and got rid of all those stupid fractions. You're welcome to borrow that if you like. The tangent of pi over 4, we say root 2 over root 2. You might be saying root 2 over 2 over root 2 over 2, or something equally as insane sounding. Now root 2 over root 2 is equivalent to 1, so instead of putting that, I could definitely have just put a 1, which I think I'll do that. It's equal to 1. Over, in the denominator. For that matter, I could just write that as negative root 3. In the denominator, we've got 1 plus negative root 3 times positive 1. All right, I cleaned up my act down there. I'm also going to take this equal sign and slide it down so it's right next to my fraction bar. There we go. And then equals. The numerator says negative square root of 3 minus 1. The denominator says 1 minus the square root of 3. Now, whatever software you're using, MyMathLab, ConnectMath, WebAssign, Hawks might have a product, I don't know. Whatever you're using, you might be able to type this in. If you're taking a test and it's a multiple choice situation, you might not see a multiple choice option with this answer because the denominator has not been rationalized. Your professor, your teacher might request or require that you rationalize your denominator. So be aware that this is a possible final answer, but I'm now going to go one step further and rationalize the denominator. I'm going to take my numerator. I could have factored a negative 1 out of the numerator. I'm being lazy and just leaving it in there. Keeping this denominator 1 minus root 3, and then I'm going to multiply by 1. And the version of 1 that I'm going to use is the conjugate of the denominator divided by itself. So that is 1 plus the square root of 3 over 1 plus the square root of 3. Now I have to FOIL these numerators, and I need to FOIL these denominators and combine like terms and stuff. So if you're only watching at regular speed, bump it up to 1.5. If you're at 1.5, take it to 2, because you already know how to do this, or just scoot the video forward. So I've got negative root 3 is here, and then this is going to turn out to be a minus 3, and then the inners are going to be a minus 1, and the lasts are going to be minus a root 3. In the denominator, there's a 1, and a plus root 3, and a minus root 3, and a minus root 9, which is equivalent to minus root 3. All right, then let's clean that up. So if you want to put a little note in there that says that you FOILed, FOIL, we did that in the denominator also, FOIL, great. And then in the numerator and denominator, we're going to combine like terms. I like to write CLT. In the numerator, I have negative 4 minus 2 times the square root of 3, or some people say minus 2 square roots of 3. In the denominator, the positive root 3 and negative root 3 canceled out. I'll combine like terms. 1 minus 3 is negative 2, and that gives me the opportunity to reduce my fraction now. The negative 4 and negative 2 are going to reduce, and the negative 2 and negative 2 are going to reduce, leaving me with a final answer of positive 2 plus a square root of 3. And I thought I was going to be writing that over a denominator, but I don't have a denominator anymore. The negative 2 canceled out. So let me write that again. Positive 2 plus the square root of 3. I sure wish there was a great way for me to determine if that's actually the right answer, because that's a lot of work. It seems like a lot of opportunities to make a mistake. Could I jump into my calculator again and make sure it's in radian mode, and first type in the tangent of 5 pi over 3 minus pi over 4 using parentheses around those angle measures? Absolutely. And then I could type in this final answer that I got? Absolutely. In fact, I'm going to do that just to double check, so I'll pause real quick. When does it become legible? It's so hard with these images being mirrored and real shallow depth of field, but there it is, so that you can see how I typed it in and how you can check and make sure that the exact answers that you're getting are equivalent to what you should be getting from the original trig function. Technology is so nice when it works. Love that. All right, let's get small and focus. Now you can see my beautiful face. this problem is, very similar in idea to what we just did in the previous problem, except we're starting with the right-hand side of the equation, or the identity, or the formula, instead of the left-hand side. In this problem, we said, well, that's tan alpha minus beta, which is the left-hand side of this equation, and we matched up the alphas and betas. In this next problem, this thing is the entirety of the right-hand side of one of those statements. Look at the numerator says tan alpha minus tan beta. And this says tan alpha minus tan beta. And the denominator of that right-hand side says 1 plus tan alpha tan beta. 1 plus tan alpha tan beta. This is almost like a two-step process. It has a numerator and denominator, both of which have to match up with the alphas and betas in the right place to confirm for us that indeed alpha is 50 and beta is 20. And once we've matched up those pieces, we can take our alpha and beta of 50 and 20, plug them into here, and write that the statement that we were given is equivalent to the tangent of 50 minus 20, which is equal to the tangent of 30, and the tangent of 30 degrees is 1 over the square root of 3, which is equivalent to root 3 over 3, if you rationalize by multiplying by rad 3 over rad 3. Here's another problem. This one is using radian measures, and it's using the other of the tangent formulas, the first one. So alpha is going to be pi over 5, beta is going to be 4 pi over 5, so this is equal to the tangent of alpha plus beta, which is pi over 5 plus 4 pi over 5, which is equal to the tangent of pi. And now you need to know what your graphs look like. You need to know the periodic nature of the tangent function. There are asymptotes for tangent. Actually, the asymptotes don't matter so much on this one. Do you know what the tangent graph looks like? Do you know what the tangent of 0 is? Do you know what the period of the tangent function is? If you know that it's pi, then the tangent of 0 should be equivalent to the tangent of pi. And if you know how to look at this diagram, at this graph, and determine that the tangent of 0 is equal to 0, therefore the tangent of pi is equal to 0, then you're in good shape. So the answer to this question is indeed 0. Can't help myself. In this example, we're to be verifying the identity. I would say that the left-hand side is more complex than the right-hand side. The left-hand side says sine of alpha plus beta. This is my alpha. This is my beta. And where am I? I had to pop back and confirm, because I don't memorize these things, that the left-hand side of this equation matches up with a sine-sum identity. I knew it was the sine-sum identity. I just didn't know what the other side of the equation looked like. So I went back and I double-checked. You're going to be using your formula sheet in order to confirm what the other side of the sine equation or the sine-sum formula looks like. And it is the sine of our alpha value times the cosine of beta plus the, I think they wrote it as the cosine of alpha times the sine of beta. And we're hoping that that's equal to the negative cosine of x. The sine of x is the sine of x. There's no more simplifying we can do there. What about the cosine of 3 pi over 2? In my head, here's what I do. I draw the cosine function and I go like this. Cosine of 0, cosine of pi over 2, cosine of 2 pi over 2, cosine of 3 pi over 2, which is equal to 0. Cosine of 4 pi over 2 is back up at 1. But I'm most interested in the third of those quarter points, or sorry, the fourth of those. No, 0th quarter point, first quarter point, second quarter point, third. Anyway, the point on the graph where x is equal to 3 pi over 2 returns a y value of 0, so the cosine of 3 pi over 2 is 0. So that whole first term is going to go away. Cosine of x is still there, and I'm really hoping that the sine of 3 pi over 2 is equal to -1. The sine function, sine of 0, sine of 1 pi over 2, sine of 2 pi over 2, sine of 3 pi over 2 is indeed -1. Sine of 4 pi over 2 takes us back to 0. And that's it. Negative cosine x equals negative cosine x. I would put my QED box there straight away. Nice job. What else? What else? So this one is sort of a different setup than we have seen so far. The part A is asking us for cosine alpha plus beta, and I should probably print out a formula sheet so I don't have to keep pausing and scrolling back to the top of the notes, but I'm going to scroll back and confirm what cosine alpha plus beta equals, and it's equal to cosine cosine minus sine sine. And then we're going to have to figure out a way to evaluate the cosine and sine of alpha and beta. Mommy just got home, so Sophie's going to go see Mom. Go get her. Go show her how you're feeling better. Go on. Go get her. So how are we supposed to evaluate these? We're going to use this other given information. We've been told that the cosine of alpha equals 1/2 and that alpha is in quadrant 4. So let me draw a sketch of quadrant 4. And alpha, cosine of alpha is equal to 1/2. So that's adjacent over hypotenuse equals 1/2. So there's my alpha in there. And the cosine of alpha, which is adjacent over hypotenuse, and by knowledge of the 30, 60, 90 triangle, I know that my other leg is equal to -√3. And then we're also being told that the sine of beta equals -1/3, and beta is in quadrant 3. So let's draw ourselves quadrant 3. Sine is opposite over hypotenuse, so I'm going to draw it not very far down into the third quadrant. We've got a -1 and a hypotenuse of 3. 9 minus 1 is 8. The square root of 8 is 2√2 in the negative direction. So we've got our diagram there. I'm going to call this beta. It's really beta prime. It's like a reference angle. Beta is actually probably there. Alpha you could think of as a negative angle measure. You could think of it as a positive angle measure that pushes you all the way around into the fourth quadrant. As long as your diagram's good, I would go ahead and label your reference angles with alpha and beta. That's what we're going to focus on. And now that we have these really nice diagrams, it's easy for us to find an answer to part A here. Let's do this one. So the cosine of alpha is, oh, we were already told that's 1/2. That's nice. The cosine of beta, so that's adjacent divided by hypotenuse. So we're multiplying by -2√2 divided by 3 minus the sine of alpha. So I'm back to the left-hand diagram. Sine is opposite over hypotenuse. So that is -√3 over a hypotenuse of 2. And then the sine of beta, again, opposite over hypotenuse, So that's times -1 over 3. And then we've got some simplifying to do. From here, it's just arithmetic. But you can see how important the development of those diagrams is. And if I can confidently develop those, then it really makes the rest of the process a lot easier. So now let's do the part that I dislike maybe the most, which is the arithmetic. So equals, these 2's are going to cancel, and I'm left with -√2 over 3. Yeah, I'm not going to do that. Because over here, the 2 doesn't cancel, which means I'm still going to have a denominator of 6, so I might as well just leave the denominator of 6. So let's do it that way. Let's start over then. We've got -2√2 over 6. And then I've got a triple negative, minus a negative times a negative, which is really like minusing a positive, which is really like subtraction. And that's still a highlighter. There we go. Minus square root of 3 over 6. Now we can put our numerators together, and there isn't really a common factor that we can take out like we were doing with those root 2's earlier. I think we can just write this as -2√2 minus root 3 all divided by 6. I think that's a very reasonable final answer. And as you know, oh, we can't really do it in this problem because we don't know what alpha and beta are. I was going to say, we could come back up here and add our angle measures together and take the cosine of that angle measure, except, well, you could try it. I'm not going to do it, but you could try it. Think of alpha as being -π/3 or +5π/3. And you could think of your beta value as being 7π/6 or -5π/6. Try it with those. Make sure that your calculator is in radian mode as you do those. Add those two angle measures together. Take the cosine of that resulting angle measure. See what you get as a decimal. Then type this stupid looking fraction into your calculator and see if you get the same decimal. And that'll tell you whether or not we have a right answer there. Hopefully they match up. If they don't match up, hey, nobody's perfect. Go back through our work that we've done here and confirm or try to discover what it is that we did that was a mistake. But I'm feeling pretty confident. The only thing that I ever get nervous about is whether or not this is correct, because they all really start to look the same after a while. All right, what else do we have? Oh, so just some more of these, and this is fine. You could use the sign of alpha plus beta equals, and then whatever the other side of that identity is, you know, sine cosine minus cosine sine or something. I have no idea. I don't memorize those kinds of things. You could try it and go through a similar process that we just went through and get some gnarly looking answer. But the good news is you can use the same diagrams that we were just using. So it should be much easier to fill these in and evaluate those resulting functions. And then again, if it worked for part A, try it again for part B. Add those angle measures together, take the sine, see what you get as a decimal, and compare that to the decimal equivalent to the answer that you got. And then you could do it again for the tangent function. And then last but not least, write as an algebraic expression, no trig functions. We're supposed to rewrite this as an algebraic expression. Assume x and y are positive and in the domain of the inverse trig functions, so we don't have to worry about any domain conflicts. That's nice. Sure, let's try this. Let's just see what happens. The inverse tan of x. I'm going to think of this as the inverse tan of x over 1, so that it is opposite over adjacent. And what happens when I take the inverse tangent of something, x over 1? Remember that the input into an inverse trig function is a unitless value, side length divided by side length, where the units cancel out. The output from an inverse trig function is going to be an angle measure. So while that is x over 1, and I'm going to call this y over 1, I'm also going to note that once I figure out that inverse tan, that's going to be an angle measure that I'm going to call, you know what, let's call it alpha. And once we evaluate this inverse trig function, the result is going to be an angle measure, let's call it beta. I see one more referencing back to page 1 so that I can find out what the right-hand side of this thing is going to look like. Okay, so we've got the sine of alpha minus beta. Let's draw a diagram of alpha and beta, much like we did in the previous series of problems with part A, B, and C. The opposite over adjacent for alpha is going to be x over 1, and x is positive, so I'm going to draw in the first quadrant. I don't want to go into a long conversation about deciding which quadrant to draw in. I'm just going to draw it. It's kind of an arbitrary right triangle that I've drawn out there, but opposite is equal to x and adjacent is equal to 1, and that makes a hypotenuse that is equal to the square root of x squared plus 1 squared, which is x squared plus 1, so we'll leave it as that. This is my alpha value. Notice that the tangent of alpha equals x over 1. This x over 1, or I should say this x over 1. Let's diagram beta. Sine, well, we're going to be in the first quadrant again. Arbitrary triangle, we're going to label it correctly. Sine is opposite over hypotenuse, so that's a y over a 1, which by the Pythagorean theorem makes the adjacent side length equal to the square root of 1 minus y squared. And that is angle measure beta. Now, what does the sine of alpha minus beta equal? All right, I'm taking you with me this time. Maybe we can spot it along the way. Sine of alpha minus beta. No, no, no. Sine of alpha minus beta. Come on. Don't make me go all the way back to the top. Tangent. It's going to make me go all the way. Alpha plus beta. Hey, alpha minus beta. There it is. So it's sine cosine minus cosine sine. Now all I have to do is remember that. Sine cosine minus cosine sine. Maybe if I just keep saying it over and over again, I'll be able to remember. All right, that was a lot of scrolling. Thanks for hanging with me. So this is equal to sine cosine minus cosine sine. Based on our diagrams, what's the sine of alpha? Sine is opposite over hypotenuse, which is x over the square root of x squared plus 1, times the cosine of beta. Looking at the beta diagram, cosine is beta diagram. It sounds kind of like betadine. Not really. Adjacent over hypotenuse, which is the square root of 1 minus y squared over 1. Now minus the cosine of alpha, which is adjacent over hypotenuse. Times the sine of beta, which is opposite over hypotenuse. Well, that's nice. We've already got a common denominator. So I'm just going to mash these numerators together. I have x times the square root of 1 minus y squared minus 1 times y, which is y, all divided by the square root of x squared plus 1. You could rationalize that denominator, but then you'd have to multiply by the square root of x squared plus 1 over the square root of x squared plus 1. Not doing it. If you want to do it, have at it. I'm gonna go have dinner or something, just take a break. I've been talking for like an hour and a half worth of videos, and I taught for 6 hours, and I tutored for 1 hour. 6 plus 1, that's 7, plus 1.5. That's 8.5 hours today of talking about the maths. I think I deserve a short break. I'm taking it. You deserve a short break too. Thanks for hanging with me on this session of looking at this first sort of cluster of identities and formulas. Keep using your formula sheet in order to make your way through your homework assignment so you're very familiar of where those formulas are on the formula sheets. And I will see you in the next section, which I have no idea what it's about, but I can almost guarantee you there are going to be more formulas. So we'll sort through those together. Until then, be well. See ya.